Welcome to this ArduPilot video. This is the second part in the debugging series about using the GNU Debugger, or GDB.
Good morning and welcome to a series of videos that Henry and I have decided to make together to introduce various features of ArduPilot. And we're starting with one that Henry asked me about this morning, which is using the GDB debugger with ArduPilot. So we've got Henry here as well. And so what we're going to do is show a little bit about how to debug ArduPilot. And I'm going to start with debugging in SITL, the software in the loop simulator. And so what I've got here is a simulated multi-rotor, and I'm using mavproxy, which is what you get by default when you run the sim vehicle command for launching SITL. And we're running it with the --OSD option, so we get the simulated OSD, because Henry was exploring using GDB to debug the OSD code. So,
and you started also with the debugger and the GDB options, right?
Yeah, that's right. So I'll show a couple of things how I launch it. One of the tricks that I tend to do, I mean, there's lots of different ways of launching it, but I tend to create a subdirectory within the vehicle type that I work in. So in this case, I've created a GDB demo directory inside the ArduCopter directory. And the reason I do that is when I then go and launch it, then all of the parameter changes and things that I make for this little session go in the eprom.bin in this directory, and all of the logs and things go in this subdirectory, and that way it keeps it separate from all of the other little experiments that I'm doing with ArduPilot. So I tend to have a whole lot of little subdirectories. So I've CD'd into that, and then I'm going to launch sim vehicle, and I'll show you a couple of things about how I'm launching it here, because it's a little bit different to what other people might do. One of the things is I always run the simulator with nice at the front. And what that does is that lowers the CPU priority of the simulator, which means it doesn't disturb my Zoom call or Skype call or whatever else I'm doing. It means that I don't get weird audio issues when I'm using lots of CPU. It's great for also when you're building ArduPilot to run it nice. It means that your build doesn't disturb your other things going on your computer. And I give the path, the relative path to sim vehicle. Other people, what they do is they edit their $path to put sim vehicle in the path. The reason I do it this way is that way it runs the sim vehicle in this particular directory. Because if I have a look on my box and have a look in my data directory, I've got lots and lots of checkouts of ArduPilot for all sorts of different purposes. And so this particular one, I want to use the local sim vehicle. So by using this relative path, it starts up in this version of ArduPilot. And so the -D is really important, as you said, Henry. So -D says to build with debugging. So that means it passes the --debug flag to configure when it builds. And -G means attach the GDB debugger. So when it launches ArduPilot, it launches it with the debugger already there and ready to go. And then --OSD and console, because we want an OSD because we're debugging the OSD code, and I want the console up, and I'll add the map as well, so we get the map. So I run it like that, and it's going to notice it's embedding all the fonts there. Up she comes.
And that right treats the -D, the debug, because there's specific lines in the code that would normally not be executed that create values and actions that are prefaced with debug statements. Is that correct?
Yeah, it's sort of two things that it does. One is you're absolutely right that it does activate some code, some debug code, but the main purpose of the -D is to build with debug symbols. Now, you can actually run GDB without debug symbols, but it won't give you all the names of your variables, and you can't look at the variables on the stack. So running with debug symbols is a lot more useful. And I actually always run with -D when I'm running sim vehicle, and usually I run with -G. And the reason I do that is because if we, for example, have some bug that, you know, just occasionally shows up, and if I run across it, I would curse myself if I didn't have -D, -G, because I wouldn't be able to then debug that rare bug. So what it's done is, if we have a look back here as to what that actually did, so I go back through my history there, and you can see the configure line that it used. So this is sim vehicle. Because I passed -D, it did it with configure --board SITL. That's what you would normally do. These double quotes are just because the way Python displays this. But it's added this --debug. And the most important thing that does is adds debug symbols, right? Which means when we put a break in, we can actually look at all the variables and display them properly. All right, so let's demonstrate that. So we've now here's our little OSD. We'll just pop the OSD down there to have a look at it in a minute. The most important window is this one here. You'll notice that this is a little X term that has popped up, right? And you can ask ArduPilot to pop it up in an X term, or you can ask it to put it in a screen window. There's lots of different ways in sim vehicle. The default is to pop up the ArduPilot, in this case ArduCopter, executable in an X-term window, and it's attached it with GDB, right? So if we have a look on the command line, you'll see that it's actually run GDB like this. So when it's executed ArduPilot, normally it would just run, you know, data APM build SITL bin ArduCopter. This run, it's running GDB -X args, and it's created this little temporary file with the options to GDB. -X means pass options to GDB, and it's turned off pagination, and then it tells it to run. All right, so there we've got GDB up. So the first thing we do with GDB here is we hit Control-C. So when I hit Control-C, that stops the program, okay? And now, this is the first little interesting quirk you get. If you don't have, so this has stopped ArduPilot. So you notice I'm getting no link up here, right? So my ground station is not getting any packets. So time has stopped, and my vehicle, if it was flying, would be paused midair. And we're now, you know, in the debugger having a look at what's happening. Because ArduPilot SITL is what's called lockstep scheduled, meaning that the time in the vehicle is independent of wall clock time, independent of the real world, which means you can stop it and single step it and do things in the debugger without it interfering with the physics. All right, so this is done a break with Control-C, and it stopped it, and it stopped it inside a system call called send, right? Because it was just in the process of sending something on a socket. And what we can do is do a BT. So I type BT for backtrace to see where we were. And if I scroll up a little bit there, then we can see we were doing a libc send, and within the libc send, that was being called from ArduPilot's socket APM send, which was being called from this little function output to flight gear. This is one of the lesser known parts of ArduPilot SITL. You can actually output it by default, outputs ArduPilot's state in a format that flight gear can see, which means you can actually visualize in 3D the copter, right, by launching a copy of flight gear. That's a topic for another day, but it was in the process of outputting that flight gear data when we stopped it. That was just by luck. So we go all the way back up, and at the top level, it's in main, right? So there it is, launching ArduPilot. That's where ArduPilot starts at copter.c line 805. So if we go into ArduPilot copter.cpp and we go to line 805, then this is the root of ArduPilot where everything starts for ArduCopter. And so it was from this line of code, it was then going into HAL SITL run, the vehicle loop, the scheduler loop, waiting for INS samples, doing delays, etc. Okay. So the first thing I tend to do is I actually go up. So there's the up command to take you up the stacker level. and I do ups until I get into the main, into our local code. Now, the reason for that is this funny quirk that you can hit. If you don't have all of the source code for the system C libraries and you try to debug in there, you can get some weird terminal issues in your Xterm because GDB, strangely enough, GDB has a bug where this, printfs from within the C library and within the debugger can cause the terminal to get all screwed up. So it's a good idea to go up a couple of levels until you're into the main ArduPilot code, right? And then the next trick is to learn how to display the source code in this window. And what you use is something called the TUI. So GDB, if you do a Google search for GDB TUI, so the TUI stands for Text User Interface. And it's a piece of ancient GDB code that allows you to see the source code in the debugger. And it's actually very useful. So let me show you that. So you hit Control X followed by A. So if I were to write that as a, debug like this, so that would be Control X followed by the letter A, right, like that. So I go Control X A, it's actually lowercase a, and that splits the screen like this. And so you've got the source code up the top, and you've got the GDB prompt down the bottom. All right, so that allows us to navigate around the source code with the cursor keys, okay, which is really handy. Sometimes it's useful to navigate in this bottom pane down here where you got the GDB prompt. And so what you do is Control X followed by O, and O stands for other, right? So O means the other window. That basically means to move the cursor. So the cursor's now in this bottom window, and if I use the arrow keys, it goes through the history of my commands, right? And it also means you get the complete GDB prompt with all its tab completion and other nice things down in that window. Whereas when you're up here, the cursors are controlling the source code movement, so you don't get the full GDB prompt capabilities. So knowing how to switch between those two windows is really powerful. All right, great. So I'll just show you how to look at some variables. The root of, this is ArduCopter, and the root of ArduCopter is this variable, great big variable or C++ object called copter. And we can have a look, if we use P for print, we can have a look at all the elements of copter, right? So if we go and have a look at copter.h, then in the copter object, we've got lots and lots of variables. And let's have a look, for example, at the vibration check object. So I can go VIB tab, right? And that's taken me into the vibration check object, and I can go tab, tab. Tab key is terribly useful in GDB. Basically, just whenever you're in doubt, hit the tab key and it completes stuff. So we can have a look at, the high, we can show that whole structure, right? Copter.vibration check, and that's showing us the contents of that little structure, okay? So we could also put breakpoints, etc. All right, but where we got started with this, so Henry was asking about how to debug the OSD. So let's go and have a look at the OSD code. And let's look at our little OSD display down here. So let's look in the OSD, the main OSD code. And in fact, let's look inside the screen code where it paints the various screens. And so what we can do, now which particular type of element did you want to have a look at, Henry?
Oh, I was just trying to pick something that had a stack variable in it.
Okay.
Look at it.
All right, so let's have a look at the draw voltage. What about the draw battery voltage? All right.
That should do it, right?
Right. So what I can do is I can just cut and paste that name like that, go back here, and I can say break on that draw battery voltage with a B command. Okay. And so now I say continue in the debugger with the C command. And now what it does is it now stops when it gets that command. Now, the interesting thing is I wanted to break at this line of code, but instead it broke at that line of code. Now, the reason it did that is because I wasn't specific. I could have asked it to do this specific function, but there's actually two functions of the same name with different arguments, and one calls the other, right? So what it's done is it's taken us down to this function, which then calls the more specific function down in here. So I can, the next thing we need to do is step into that function. So S steps into a function and N goes to the next line. So let's step into that function. There we are. So we're now stepped in. I used Control-XO to move the cursor. So there I am in this one. And I can go next, next, next. And we've got all these variables here. These nice little variables, V and battery and blink volt, right? So one of the useful things you can do in GDB is show all your local variables, info locals. Okay, so info locals shows us all of the local variables we've got here, right? That saves time with, typing the individual variables. And some other useful things, let's put a breakpoint at the current line of code. So in fact, we'll delete all the other breakpoints. So delete all breakpoints, but add a new breakpoint just with B, and that puts a break at that line of code.
So we use the D. What about clear?
You could clear. D just means us to delete, and then the default is delete all breakpoints, which is really handy because often you've got too many breakpoints all over the place. You can do help, so you can go help clear. Often when you're asking for help, it's useful to go Control-XA again, and the Control-XA gets rid of all of your, displayed
the split screen.
Split screen. So I can go help clear to get help on the clear command. So that clears a breakpoint at a specified location, tells you all about how to use clear. Most commonly, you just use D. IB is what we want. IB, info breakpoints. There it is, info.
Okay.
Okay, there you go. I've learned something from this. Thanks, Henry. So that's our breakpoint we've got there at that particular line of code. Okay. So if I ask it to now continue, then it will stop at that line of code. All right. So I can go continue, 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 and it'll keep going until that line of code, right? So now something very useful is display. Display adds, so we've got a print. So we can go, let's do a print first. So print PCT. Okay, so that shows that PCT is currently 100, right? Because my battery is full, right? And you can see it up here. It's showing 100% full on my battery up there, and that's that percentage that it's got, all right? But if we go display of P, display percent, what that will do is when we continue, all of our current displays get shown whenever we hit a breakpoint. And so that's a really useful way of instead of pre-printing it each time, you set up a display on a breakpoint. All right. So what we're going to do is we are going to let's do a conditional breakpoint. So we've now just broken at breakpoint 2, and I'm going to go cond to PCT less than or equal to 98. All right. So what that does is says add a conditional for this breakpoint, meaning this breakpoint will only activate when the battery percentage is below 98. Okay. So if I go continue now, then what it will actually do is it will actually stop at that line of code each time. Then it'll evaluate that little Boolean PCT less than 98. And then if that is true, it will stop.
Why condition 2 versus condition 1?
Because this is breakpoint number 2. Because condition says which breakpoint number, and this is because I had a previous breakpoint 1, this is now breakpoint 2. And so if we go continue, right, now our battery is still at 100. Okay, so how are we going to, let's go and do a takeoff. So mode guided. And let's set, one of the most common things I do is I turn off the disarm delay to set it to 0. That way I can set a very large speed up. I should say, by the way, I've got this alias speed up, which allows me to raise and lower the speed up really easily, because I've got all of these aliases.mavenit.scr, and I've got a little speed up there. Actually, there it is. Alias. So alias add speed up is param set sim speed up, and that allows me. So if I just go speed up, that's the equivalent of param set sim speed up, and that displays it. But if I go speed up 20, then that means that it's changed it to 20. All right, great. So we're now to speed up. So I'm going to arm the throttle, and then I'm going to take off to some high altitude. Great. Aha. So now we've hit the breakpoint, right? So because our battery it's still showing 99 here because it was just dropping to 98, right? And you notice that if we do, we can see that display we had, PCT is now 98. All right. Now we could change that conditional, say 90, right? And continue. And so now, there we go, we've hit 90% battery, right? So it's now activated, okay? So that's a way of setting, that's really, really useful. Now, there's another thing we could do. So we could, it's really useful to be able to put in what's called a watch point. And there's a difference between a watch point and a breakpoint. So a breakpoint is associated with a line of code and can have conditionals on it as to whether the breakpoint should activate.
Just to interrupt you, can you actually
sure.
set a breakpoint at a line of code rather than at a function call?
Yes, in fact, that's very, very useful. So if we put breakpoint on APOSD screen, and the nice thing about it is as long as it's unique, you don't need to give the full path to line of code. You don't need to give it libraries APOSD screen.cpp. And the syntax is the file name : the line number. So let's put a break at this line 1321. Like that. So we've now got a third breakpoint, breakpoint 3. We've deleted our first breakpoint. So if we go IB now, we've now got the 2 breakpoints. And if we continue, it'll now stop at that 1321, right? And in fact, that's one of the most common ways of doing it, putting a break at a line of code, because you often don't want the entry to the function. You often want a specific line of code. All right. So now we can go inside this. We see where it's calculating the battery percentage. If we do S, that means to step into the line of code, whereas N, so if I do an N now, the cursor moves to the next line of code, right? Now I'll go continue again, and I'm back at this line of code. If I do S instead of N, it'll step into this capacity remaining PCT function. Right, so let's step into that. Great, and so it's taken me, that's actually in a header file, okay. And if we put the cursor in the top window with Control-XO, and we can scroll across, then that function is a header function that just calls capacity remaining percentage with the primary instance. So we can now step into that. Right, so we're now inside that function there in the header file. We go S again, and now we're inside this battery remaining percentage up here with an instance number, right? And we can step into that and then step all the way into that back end function, into the analog battery monitor, right? So we're now in APBAT monitor back end, right? Which is, and it's looking at the pack capacity, and then it's going into the value because that was looking up. If we go up there, then you see this params.pack capacity. that looks like it's just a variable, but pack capacity is actually an AP param, right? So if we do p of underscore params dot underscore pack capacity, that's actually an AP param, which when you get the value, do this comparison, it actually needs to look at this underscore value entry in the param, which is why when I step into that, it actually shows me this little operator underscore value here, returning the value for this in the parameter library. Okay, so we step on that and we're now back to this line of code and we can see, what it's doing. And finally, it's going and calculating the milliamp hour remaining and getting the percentage. And we can have a look at all of those local variables, right? Info locals. And there's only one local variable that we've created, which is this milliamp remaining. Yes, we're going to talk about watch points. So let's go and have a look at, so let's see, say we wanted to know who is it that updates this, in a battery backend, right? So in our battery backends, every battery backend inherits from this class, and it's got these variables here, right? Which is like current max amps, voltage filtered, resistance voltage, resistance timer, all of these sort of numbers, okay? And we could look, for example, at, we could try to see who is the one that updates voltage filter, right? Say, for example, you're getting a weird value and you want to know who's setting that weird value. Where's that coming from? Oh, one of the things I'll show you is how to dig your way down into the ArduPilot libraries. And there's a couple of ways to do that. One of the most useful is to use the singletons, because you'll notice that the battery monitor has what's called a singleton, because we only got one battery monitor. That's what singleton means. There is just one of it, right? So we can have a look at AP bat monitor singleton, right? So that is the pointer to our battery monitor. Okay, so we can go within that, and so we've got a set of drivers and state, right? So it's got this bat monitor state and these set of drivers. So let's have a look in the drivers. Okay, we'll look at our first driver. So the first driver is a battery monitor backend, right? Like that. And let's have a look in the back end and have a look at this voltage filter variable, right? So, and if we have a look at the voltage filter, there's our voltage filter variable. Okay, now notice that when I've printed that, I could have printed that from within a function that could see it, but I'm printing it up here and I'm using its a fully qualified name. So in other words, this variable here, this great long expression, that expression is valid no matter where you are in ArduPilot. Okay, because it's starting up from a global variable, which is this singleton, and then going down into the voltage filter. So when you've got an expression which is globally accessible, you can go and put a watch point on it with like watch of that variable. Okay, and notice it says it added a hardware watch point, right? Now a hardware watch point, they are wonderful things. And on a desktop CPU, this is an x86-64 CPU. On this CPU, it's got lots of hardware watch points. And the great thing about hardware watch points is when you add a hardware watch point and it's waiting for that variable to change, it doesn't slow down the program at all. All right? It runs at full speed, and the CPU has recorded the fact that we're interested in stopping whenever that variable changes, right? And so the other type of watch point is a software watch point where it has to evaluate it each time, and that's very slow. All right, so we can now go continue, and you have requested too many hardware breakpoints, watch points. Okay, let's get rid of all of our breakpoints. I thought we would have plenty. No, it's still okay. It's being problematic. What I'm going to do now is show you a trick. When GDB doesn't like you doing that, what I'm going to do, I'll just get rid of that, and I'm going to show the address of this variable, voltage filt, like that. So notice that this gives you the address in memory of that variable. Okay, and so I'm going to now delete all our breakpoints and watch points, and now I'm going to watch. Now, look at this line here, $8 equals $. So whenever you print something, it assigns it a variable number in your history. And you can refer to that. So I can P $8, right? And that shows me that. I can also P $7 and $6. So they're all the variables I've looked at previously. Okay, but what's really, really useful is I can watch $8. Now what that does is that sets up a hardware watch point on this direct memory address, right? And the star means the dereferencing of it. So I'm saying, tell me when the contents, because the star dereferences it, the contents of that memory address change. So let's do that as a hardware watch point, right? And now it does show me whenever that changes. Now, interestingly, that doesn't appear to be changing, that variable. Okay, let's see why that is. Voltage filt. And we actually expect it to be changing there. All right. Update resistance estimate. Let's see if that's actually being called. Okay, we are calling update resistance estimate. And we are going down here. And we are, so let's see if voltage built, that's 12 points. So, and then we'll run that line of code. The thing is, it's coming out as exactly the same variable. So I can P $13 minus $12, and it hasn't changed, right? So that's why it's the variable hasn't actually changed. The hardware watch point isn't triggering because we're not changing the value. Okay, so how could we get the voltage filt to change? If I delete that breakpoint number 7, and if we change that filtered voltage, what could we do? Mode loiter RC3. There it is, it's changing, right? So we descended rapidly, and this filtered voltage now has changed, and it's showing us the old value, 12.5879793, and the new value is 12.5879784. So it hasn't changed very much, right? But a hardware watch point will show you any change, okay? So just as we were hitting the ground, right, that filtered voltage changed, and that showed us the change in value, and it shows you the old value and the new value, right? Now, sometimes you can put hardware watch points on that full path expression. In this case, it wouldn't let me. I don't know exactly why, but the trick you use is you get the address of it, and then you watch the change of that address. And that sets it up directly as a hardware watch point on that address. Basically, that 64-bit pointer gets lodged in the microcontroller, in the CPU on my laptop in this case, and that says, whenever the contents of that piece of memory change, stop and enter the debugger.
Well, you did that on something that was globally
Yes.
available, right? So what about watching something happening inside a function or something?
Yeah, very good point. So let's go and find. Now, that's slightly trickier. Okay, so what about this little variable current delta, right? That variable here on the stack. So if we go and let's break on this line of code. So I'm going to delete all my breakpoints to start again. APBAT monitor backend .cpp : and line 66. which is where I am. And there we are now with a break at that line of code. All right. And we can look at current delta, and that is minus 13. But the thing is, if we look at the address of current delta, right, that address there, you're probably a bit hard to read that font, 7FFFD180. If I look, just get out of this and info registers, right, this is all of my registers that I've got. And my stack pointer, where's my, stack pointer. So my stack is around this 7FFFF, mark. And this variable that we're looking at, if I look at that, is inside that stack, right? So this is what's called a stack variable. Okay, so its address is, the variable only appears, it's only what's called within scope when I am inside this function. So if we can put a hardware watch point on that, right? We can go and stick a watch point. So if we print that variable and we can watch star $18, perfectly legal in the debugger, but not particularly useful. Let's see what happens.
Stack is always changing.
Well, it's that it gets reused for other functions, right? So if I go continue, okay, then the new value, the value changed from minus 13 to 0, right? But it changed back when up inside this logging function, because that logging function just reused that piece of stack, okay? So the variable then changed, which means it usually isn't useful to do a watch point on a stack variable. You can, however, put a... Yeah, sorry, Henry.
Can you put a little piece of code in the function? Like,
yeah,
I debug a lot with syntax messages, which is kind of clumsy, but it allows you to dump out stuff to where you can see it. Can you create something that becomes a globally watched
indeed, and that's a really good idea, because you could do this with a conditional breakpoint. Okay, so let's do it with the conditional breakpoint first. Let's delete all our breakpoints, and then we'll break at ap bat monitor. Notice I'm using tab, right? Backend.cpp to tab complete there. Line 66 again. Okay, so we're there, and we could put a conditional breakpoint number 10, and current delta less than minus 13, right? Because the value we were getting for current delta was around, okay, it's minus 10. Let's say, greater than minus 10, something like that, okay? And what it will do, and there it is, it's now done a break. So we ended up with a current delta of minus 9.0, right? So that allows us to build a conditional break. But the problem with it is, particularly if you're debugging on hardware, like if I was debugging on a board with a hardware debugger, those conditional breaks are quite expensive, and they slow down your program, because what has to happen is the debugger always stops at that line of code, and then it has to evaluate that expression, right? So it has to actually go and ask the CPU for all the variables that are needed in the expression, and evaluate the expression with a little evaluation function, determine if it's true or false, and then decide if it's going to break or not. Now, that means it slows down your program and disturbs it. But we could instead do something like change the code if current delta less than, or say greater than minus 6, and then we could put a line of code here, which which will execute only on that, and we can put then a breakpoint on that line of code, right? And that won't slow down the program, okay? And all you need to do is call any function which the compiler is not going to remove for you. So we can call something like ap-hal millis in there, right? Like that. And so let's go and rerun this. And one of the tricks you can do is you can add a -B on the sim vehicle, and you can put a line number. So I can put, just like the breakpoints, so monitor backend.cpp : and I'm going to put line 70, which is where that millis is, right? So I can actually launch sim vehicle. I'll just make this a bit wider so it's easier to see. So I'm launching sim vehicle with a breakpoint. So -B tells sim vehicle that when it launches GDB, it should add that breakpoint right from the start. Okay,
Mm-hmm.
this is particularly useful if there's some problematic line of code that causes it to crash right on startup. Then you can say, okay, break on that right at the beginning. All right, so that's now launching sim vehicle, and it's going to recompile that line of that that's a single file. Great, and then it's started up, and there's our GDB. Now that GDB that's running at full speed, because that breakpoint, that breakpoint being there doesn't slow down the program at all, right? So let's go mode guided, arm throttle, takeoff 100. There you go, it's just happened, right? So we've hit that line of code. I now do the Control X followed by an A. So I'm now got the cursor there, and I can now P current delta, and indeed it's 1.2, right? And we can see that it's met that condition. It's greater than -6. And so it then executes that line of code. So that's a really handy way of working, because it's very fast. It doesn't slow down the program at all, and it allows you to take your debugger right to the place that you want to see what's happening. All right?
And more
Okay.
importantly, you're setting a breakpoint on something that's not global.
Indeed.
A variable that's not global, which would be problematic otherwise.
Indeed, that's exactly right. So it's a really handy way of doing that. And you notice things like the OSD, is frozen while I'm doing this. Now, I'll share a couple of things. So ArduPilot,
Just a note on the
yep,
OSD panel, sometimes you'll get an exception from the operating system that says the OSD is not responding, or panels like that you've created in the thing, you force or wait. You just hit wait or don't, or just ignore it, and when it starts up again, it'll be fine.
Yep, indeed. Okay, so let's have a little bit of a look. I'm going to show you now threads. So ArduPilot's multi-threaded. Now, on a flight controller, something like this sort of flight controller, right? It has lots and lots of threads, because ArduPilot, the principle of the architecture of ArduPilot is we are a thread per bus, right? So there's a thread per UART, a thread per SPI bus, a thread per I2C bus, etc. Okay, so in other words, the threads are associated with entities that can block, because buses can block, right? When you do an operation on a bus, that takes some time. So we do a thread associated with each bus, right? Plus there's a main CPU, our main computation thread for actually flying the vehicle. Okay, so now in SITL we have a lot less threads, but there are some. All right, so if we have a look here, I'll just make this a bit bigger so you can see it. So you can see that we've got a few different threads here running inside ArduPilot, okay? And we can see the status of each of those threads. Now, most of these threads are just in sleep. So this thread is sleeping, and there's another thread that's sleeping, and another thread, all these threads that are sleeping, okay? And so what we can do is we can actually change which thread. So if we have a look in this thread, so this thread is our main thread, right? Thread 1. If we go thread 2 and look at backtrace, then this thread is inside our OSD update thread. So this is from start thread here. So in other words, if I show the code
Can you
here.
explain a little bit more about what backtrace is?
Oh, sure. Okay. So backtrace says show all the functions, the calling chain. All right. So if we go back to thread 1 and show backtrace, then it shows how you got to this line of code. We're currently in this update resistance estimate function, where that little breakpoint hit that we put in here, where we broke on that line, that was called from this function, read, which is at this line of code, this AP bat monitor 479. That was called from copter update bat compass, which in turn was called from this functor, right? Functors are a way of us wrapping up a function pointer with its arguments, which in turn was called from the scheduler, which in turn was called from the main loop, and which is called from the vehicle loop, which is called from all the way up to where the program started. Okay. But if we show thread number 2, right, and we backtrace that, then it is currently asleep, and it is being called from up inside the OSD here, OSD SITL 176. So if we go and have a look at OSD, and we'll have a look at the OSD SITL line 176, you'll find that that is our SITL update thread. So we have a separate thread that is running this OSD. So this is the one that's repainting the OSD.
Do the backtraces only work from a stop at a breakpoint from where you stopped at a breakpoint, or can at any time you Control-C and stop the execution of the program?
Oh, anytime.
Backtrace.
Anytime. Okay. We could delete all breakpoints, right, and go, and then there it is running. Okay, so there's the copter climbing up to 100 meters, right? And if we hit Control-C, then basically you pay pot luck. You know, where it stops is whatever you hit the Control-C. So if I now do info threads, okay, that shows where all the threads are, right? And one of them, the main thread, is currently in restrict ID type array, and it's doing stuff in the compass mag state, right? Whereas this second thread, the OSD, is down here. Third thread, we can sort of have a look at what each of the threads is doing. Now, there's a lot more threads if we attach to the debugger on a real flight controller. Because then we don't use as many threads in SITL as we do on real hardware. And that's to maintain the lockstep scheduling behavior of SITL. So there are all our various threads. And so this one, CPPM listener, looks interesting. So let's switch to thread 5 and do a backtrace, and we can see that that is, if we have a look at the start thread, so and up, start thread, clone 3, and okay, that's showing us all at the start. So we've got this thread called CPMM listener. CPMM. Now, that doesn't look like that is actually part of the ArduPilot source code. So if I do git grep CPMM on our code, there's no mention of it, right? So that is a system thread. And that is, I'm actually curious as to what that does. So let's go and see whether Google will tell us what CPPM listener is for. And let's see, it's probably part of the libraries that we link in for the OSD. So my guess is that CPPM listener, yes, you can see here, there's stuff in NVIDIA GL Core, right? And you can see it here in the backtrace. This is NVIDIA GL Core. So that is a library that is we're linking into, right? And that thread was being created by that NVIDIA display library, right? So we didn't create that thread in ArduPilot. That's a system thread that got created by the system libraries that we're linking to in order to be able to display this OSD window. All right, so you can be a little bit fooled sometimes. You can sometimes have threads under the hood that aren't something you've explicitly created, because a lot of low-level system functionality in Linux is actually implemented under the hood with a thread. Okay. All right, so what else do we want to cover in this sort of introductory session? Do we want to dive into debugging a piece of hardware, or just stay to SITL for this session? Oops, I've lost your audio, Henry. Suddenly it's gone all quiet.
That's because I muted my mic. Sorry.
Ah, right, no
Uh,
worries.
so yeah, I think we should just call a close to this
Okay,
and SITL it. I mean, and what I'll try to do is create some summary slides to follow this video up, cheat
great.
sheets and a little more explanation, and maybe a document of those slides.
Yep,
So somebody can have a little simpler cheat sheet with maybe some more words around it rather than
yep,
just
fantastic.
that.
That sounds
And
great, Henry.
I
Uh,
appreciate the time
Yeah,
and
so we'll
thanks.
call it a close, and thank you all for watching. I hope you've enjoyed it. Hope you enjoy some debugging in ArduPilot in future. And Henry and I are thinking of doing some more little videos like this around sort of log analysis and other things.
Mhm.
And so do let us know in the comments on the video if there's something in particular that you want to see. So thanks everyone, and talk to you again. See you later, Henry.
Yep. So to summarize, to set a hardware watch point to see if that variable, or really the contents of the address of the variable, actually change, and then break execution, use the watch command, either with the variable name or with a dereference to the actual address using the asterisk operator. You can also use the stored previous print values using the $sign and whatever the number was assigned for the print variable. It's best to only use these on global variables, not local stack variables, because that space gets reused by other variables as it goes through and steps through other routines. So on global variables, the space is reserved. So watching for it to change is valid.